Alright guys, hopefully you have finished your conservation of energy lab or at least collected all your data. And now we are going to do a few more conservation of energy problems similar to the ones we did last class. So before we get started, note that your homework is to complete the lab. It will be due Tuesday. If you have any questions on what you did today or any issues, you can talk to me on Monday. You also have the conservation of energy worksheet. You picked this up last class, so you should already have it. If not, you can get an extra from Mr. Jackson or email me for an extra copy. But I want to make note, as I told you in class the other day, you also will have the notes that you're taking on this video checked for a grade as well. So please make sure you watch this video and you fill out the notes thoroughly to receive your grade for that. So without further ado, let's get started. So, conservation of energy practice number 4. A 250 kilogram roller coaster passes point A at 1.7 meters per second. If the speed of the roller coaster at point C is 12.4 meters per second, how much energy is lost due to friction from point A to point C? Like we discussed in the last class, before we do anything, we need to determine, will energy be conserved in this system? The answer here is no. There is a non-conservative force acting, friction. This is implied by the statement of how much energy is lost due to friction. They are telling us that some amount of energy is lost due to this non-conservative force, and they want us to solve for that. So because of that, energy will not be conserved, so therefore we will set work equal to change in energy. We will not set change in energy equal to 0 because energy is not going to be conserved here. So we will take the work equals change in energy equation. Change in energy will be energy final minus energy initial. So the mechanical energy final will be made up of kinetic energy, elastic potential energy, gravitational energy, as will the initial. So we set it up like this. As we've done with other problems, we will next determine if anything doesn't exist or we can set it equal to 0. Well, on this coaster, there's nothing elastic going on. So we can go ahead and cross out elastic potential energy, both final and initial, because they do not exist. The next thing, if we go ahead and set our height final at 0, so if we make our reference height 0 at point C, that will help us eliminate UGF. Because if height final is 0, UGF will be 0. This, however, will make the height initial 63. How did I get that? Well, this height is 75 and this height was 12. So the difference between those, if you say 75 minus 12, you'll get 63. Okay, so we will have UGI because we have an initial height. Okay, it says the roller coaster passes point A with a speed, so there is a K initial, and it also passes point C with a speed, so there's going to be a K final. So this will reduce to change in energy equals kinetic energy final, so I'm plugging in the equation here, 1/2 mv final squared, minus parentheses K initial, kinetic energy initial, which is 1/2 mv initial squared, plus UGI, gravitational potential energy initial, which is mass times gravity times height initial. So the next thing you'll see is me plugging in the numbers into this equation. So our mass is 250 kilograms. The final velocity is 12.4 meters per second. Make sure you square that value, minus 1/2 the mass of 250 kilograms, the initial velocity of 1.7 meters per second. Again, make sure you square that, plus the mass of 250 kilograms, the acceleration of gravity, which is 9.8 meters per second squared, and the height initial, which is 63 meters. If you simplify that out, you get 9,220 joules minus the sum of these two values, which is what these two things come out to, and you get negative 135,491 joules. Now, you get a negative answer. What does that mean? That means the change in energy was negative or energy was lost. That makes sense because the problem says how much energy is lost due to friction. That's why we get a negative answer. It's telling us that much energy was lost. So if you get a positive answer for work, that means energy was added to the system. And if you get a negative answer, energy is removed. So energy in this case is being removed due to friction. Okay? All right, next problem. A 1,430 kilogram car is initially at rest on level ground when the engine exerts a force of 4,000 newtons over 95 meters before the engine cuts out and the car begins to roll up a hill. First question we always need to ask, will energy be conserved in this system? The answer is no, because there is an applied force. So there is going to be work being done over these 95 meters. The work is going to be done by an applied force. From this point on, energy will be conserved. But because there is some point in the problem where energy is not conserved, the answer is no. There is a non-conservative force acting. That force is an applied force. So energy will not be conserved. Therefore, we will set work equal to change in energy. We will not set change in energy equal to 0 because it's not a conservative system. So the next thing they ask is, what final height will the car reach? So we'll set up the work energy theorem. Work equals change in energy, and here is the equation we've been setting up before. So is there anything we can get rid of or cancel out? Well, there's nothing elastic in this problem, so we can cross out both UE's because they do not exist. The next thing we can do is cross out UGI because obviously this car starts on the ground, so height initial will be 0. The car is initially at rest, so VI is also 0. So right here, before it was starting to push, it says the car is initially at rest before the force was exerted, so we can say VI equals 0, so KI equals 0. And once that car reaches its maximum height, the velocity at that point will be 0. So the final velocity will also be 0. So if you can tell, what we're left with is just UGF minus 0, which will be UGF. So we just have work equals UGF. But there's a problem. We don't have the height in this, and we don't know what the work is. But we do have another equation for work. If you remember from way earlier in the unit and what we kind of did on our quiz, work equals F delta X. This work is the work being done by the non-conservative force, which is this applied force. So if both of these things are equal to work, we can set them equal to each other. So we end up getting this. F delta X, which that F they're talking about is the non-conservative force, or the applied force, equals UGF, and UGF is equal to mass times gravity times height final. So you can see both of these two things, we had UGF equals work from this up here. We knew work equaled F delta X from our equation sheet. We have that equation for work as well. So we can set those two things equal to each other, and we plug in the gravitational potential energy formula, so we end up with this. Plugging in my values, FAP is 4,000 newtons. Notice I use all of that force because it is all parallel to the displacement. The distance over which that force is applied is 95 meters, and that will be set equal to the mass of the car, which is 1,430 kilograms, gravity, which is 9.8 meters per second squared, height final. Once I solve all that out, I end up with 27.1 meters. So that car, once it starts coasting, we're going to assume a frictionless track. I didn't say that, but we will assume frictionless because it didn't say that there was any friction involved. It will reach a height of 27.1 meters. The last part of this question asks, if the hill in part B had been steeper, how would it affect the final height of the car? The answer is the same height. It would not affect it. It would go to the same height it did before. Notice nothing in these equations that we used was dependent on the angle or the steepness of this hill. All it depended on was the height. Now, if there was friction on this hill, the angle would make a difference because if it was steeper, it would have to go less distance to get to a certain height, whereas if it was a less steep hill, it would have to go a farther distance, and therefore friction would act over a longer period of time to get to a certain height. But in this problem, there is no friction on the hill, so no matter the angle or steepness of the hill, it will reach the same height. Now, I'm bringing back this slide just because we're about to deal with elastic forces again in this next problem, and I want you to remember, we cannot solve for the work done by an elastic force using this equation. We can use this for with FAP and FF, but we cannot use it for elastic force because it assumes when we use this equation that the force is constant and elastic force is not. Just keep that in mind when we do the next problem. So last problem we're going to look at, a man pushes a 10.5 kilogram crate from rest with a force of 67 newtons for 5.3 meters. The spring on the wall has a spring constant of 73 newtons per meter and the floor is frictionless. What is the velocity of the cart when the spring is compressed 1.2 meters? Will energy be conserved in this system? So is there applied force or frictional force? There's no friction, but the man is applying a force to the box. Therefore, energy will not be conserved because we have a non-conservative force acting, that applied force. So we will set work equal to change in energy. We will not set change in energy equal to 0 because there are non-conservative forces at work. So when we set up the work energy theorem, because that's what we're going to use here, we need to determine if there's anything we can get rid of or eliminate. All right, the first thing we're going to look at is gravitational potential energy. If you notice, it says, or it shows in the picture that the floor is level. So whatever the height is initially, it's the same height at the end. So height initial is 0 and height final is 0. Therefore, they're constant, so they can be crossed out. On your tester quiz, if you had put h equals 0 for both of these and that's why you crossed them out, that would have been totally fine. The next thing we're going to look at is it says the man pushes the crate from rest. So this crate initially starts from rest, so that means Ki will be 0 because the initial velocity is 0. The next thing we'll look at is elastic potential energy. We do have elastic items in this problem because we have this spring here against the wall. And at the beginning of the problem, the spring is not compressed. It's just resting naturally against the wall. So UEI will be 0 because delta X initially is 0. There's no compression or stretching of that spring at this moment. All right. It asks what velocity will the cart be moving when the spring is compressed at the end. So that implies there's some velocity at the end. And they're asking us when the spring is compressed 1.2 meters. So there will be elastic potential energy at the end as well. So this equation simplifies down to work equals K final plus UE final. So kinetic energy final plus elastic potential energy final. But we've got work in this problem being done by a non-conservative force, so we also need the equation for work. Work is F delta X. Now this work being done is due to this applied force. So that F right here is going to be the applied force. All of that force is parallel to the displacement, so we can use all of it when we plug it in here. So because both of these equations are equal to work, we can set them equal to each other, and we end up with this. So FAP, delta X, again, we're using FAP because that's the non-conservative force doing the work, equals K final plus UE final, and then I went on to break that apart into its equation. This is the kinetic energy equation, and this is the elastic potential energy equation. So plugging in for this equation right here and this equation right here, we get this. So FAP is the 67 newtons. Delta X is 5.3 meters equals 1/2. The mass is 10.5 kilograms. V final is what we're looking for. We got to make sure and keep that squared there. Plus 1/2. K, this is little k, not big K. That's our spring constant. That was given in the problem, 73 newtons per meter. And delta X, it's going to be compressed to the right here because that box is going to push it against the wall. So it's a positive 1.2 meters because they asked for the velocity when that's how much it's compressed. And notice that quantity is squared as well. So when we do our algebra, we multiply this together and get this value. Multiply this, get this. Multiply this and get this. So the next thing we'll do is subtract the 52.56 to the other side. And we're left, and then divide. So we subtract the 52 from the 355 and we get 302. Then we divide the 5.25 and that will be set equal to V final squared. Then we will square root And so first thing I showed you was this divided gives you this value. A joule is a Newton times a meter. A Newton is a kilogram meter per second squared. You cancel out the kilograms and you're left with meters squared per second squared. So now when we square root, we are left with 7.6 meters per second. So if that man pushes that box with a force of 67 newtons over 5.3 meters and then lets go, and at some point, as long as the floor is not frictionless, at some point it hits a spring with this spring constant. When the spring is compressed 1.2 meters, the box will be going 7.6 meters per second. All right. Hopefully that's helpful. Your homework is a combination of the types of problems we did in this lesson and the types of problems we did after your quiz in the last class. I will be at school on Monday. If you have any questions, I'm also happy to answer email over the weekend. Good luck.